Welcome back to AI Explained, everyone. I'm Leo.
And I'm Clara. So glad to be back for our third episode in the series.
Today, we're diving into what might be the most revolutionary approach in artificial intelligence of the last decade, deep learning. We'll explore neural networks, why they're so powerful, and the incredible breakthroughs they've enabled.
I'm particularly excited about this one because deep learning is behind so many AI systems people interact with daily, from the voice assistants on our phones to those incredibly realistic AI-generated images showing up everywhere.
Exactly. And what's funny is that just last weekend, I was trying to explain to my mom how these systems work, and I found myself drawing little circles connected by lines on a napkin at brunch.
Oh no, you didn't subject your poor mother to your famous napkin diagrams again. Remember when you tried explaining blockchain to my sister at that dinner party?
Hey, that diagram was a work of art, and she said it was helpful, I think.
Sure, if by helpful you mean she nodded politely while secretly texting me under the table asking what was wrong with you.
Ouch. Well, hopefully I'll do a better job explaining neural networks to our listeners today. Let's get started. All right, so to understand deep learning, we first need to grasp the basic concept of neural networks, which are the fundamental building blocks of deep learning systems.
And these are inspired by the human brain, right?
That's right. Neural networks are loosely inspired by how neurons work in our brains. The key word is loosely. They're not exact replicas. A biological neuron in our brain receives signals from other neurons, processes that information, and then either fires its own signal or stays quiet.
So how does that translate to artificial neural networks?
In artificial neural networks, we have mathematical entities called neurons or nodes that receive inputs, apply weights to those inputs, which basically determine how important each input is, and then produce an output based on all that information.
Weights, huh? So some inputs matter more than others?
Exactly. Imagine you're deciding whether to bring an umbrella today. You might consider multiple factors: the weather forecast, how cloudy it looks outside, whether your knees are aching, which my dad always claimed was his personal rain predictor.
My grandma had a similar thing with her elbow.
Family weather forecasters aside, some of these factors are more important than others. The actual weather forecast probably matters more than how your knees feel. In a neural network, these relative importances are represented by weights.
Gotcha. And I'm guessing there's something that determines whether the neuron fires or not, right?
Yes, that's called the activation function. After a neuron processes all its weighted inputs, this function determines the output, whether and how strongly that neuron activates.
So what makes a network deep then?
Great question. A deep neural network simply has multiple layers of these neurons between the input and output. We have an input layer that receives the raw data, like pixels of an image, then several hidden layers that process the information in increasingly abstract ways, and finally an output layer that gives us the result, like this image contains a cat.
And why does depth matter so much? Why not just have one really wide layer with tons of neurons?
That's the fascinating part. The depth allows the network to learn hierarchical features. In a face recognition system, for instance, early layers might detect simple edges and shapes, middle layers might recognize features like eyes and noses, and deeper layers might recognize features like eyes and noses. And deeper layers can identify whole faces or even specific expressions.
So each layer builds on the previous one to understand increasingly complex patterns. That's actually pretty elegant.
It is, and that's why deep learning has been such a game changer. These multiple layers allow neural networks to learn incredibly complex patterns that would be impossible to program explicitly.
So now that we understand the basic concept, what are the different types of neural networks? I'm guessing there isn't just one standard design.
Absolutely not. There are several specialized architectures designed for different types of problems. One of the most common is convolutional neural networks, or CNNs, which have revolutionized computer vision.
Those are for images, right?
Exactly. CNNs are specifically designed to process grid-like data, such as images. They use special layers called convolutional layers that apply filters across the image to detect patterns regardless of where they appear in the image.
Could you break that down a bit more? What do you mean by filters?
Sure. Think of filters as pattern detectors. One filter might detect vertical edges, another horizontal edges, and others might detect more complex patterns. The CNN slides these filters across the entire image, checking for these patterns at every location.
That makes sense. What about data that has a time element, like text or speech?
For sequential data like that, we often use recurrent neural networks, or RNNs. Unlike standard neural networks, RNNs have connections that loop back, allowing them to maintain a kind of memory of what came before.
So they can remember context from earlier in a sentence when processing later words?
Exactly. Though traditional RNNs struggled with long-term dependencies, basically remembering information from far back in a sequence. This led to variants like LSTM, long short-term memory networks, that are better at maintaining information over longer sequences.
I've also heard a lot about transformers lately. Aren't those behind models like GPT?
You're spot on. Transformer architectures introduced in 2017 have been revolutionary, especially for language tasks. Unlike RNNs that process sequences one element at a time, transformers can process all elements of a sequence simultaneously.
That sounds more efficient.
Tremendously more efficient and effective. They use something called attention mechanisms that allow the model to focus on different parts of the input when producing each part of the output. For instance, when translating a sentence, a transformer can look at all words in the source sentence when generating each word of the translation.
What about those AI systems generating images from text prompts? What architecture do they use?
Many of those use generative models like GANs, generative adversarial networks, or more recently, diffusion models. GANs pit two networks against each other, a generator that creates images and a discriminator that tries to distinguish real images from generated ones. Through this adversarial process, the generator gets better and better at creating realistic images.
Almost like having an art forger and an art detective constantly trying to outsmart each other?
That's a good way to think about it. And diffusion models, which are behind systems like DALL-E and Stable Diffusion, work differently. They learn to gradually remove noise from a completely noisy image until a clear image emerges. It's become the dominant approach for text-to-image generation recently.
So once we have these neural network architectures designed, how do they actually learn? I'm assuming they don't just magically know how to recognize cats or generate images.
No magic involved, though sometimes it almost seems like it. Neural networks learn through a process called training, and the key algorithm behind this is called backpropagation.
Backpropagation. That sounds intimidating.
It's actually a beautiful concept once you understand it. In simple terms, backpropagation is how the network learns from its mistakes. Let me break it down. First, the network makes a prediction based on its current weights. Then we compare that prediction to the correct answer and calculate how far off it was. That's the error.
Okay, so we know how wrong it is. Then what?
Then comes the clever part. The algorithm works backward through the network to figure out how much each weight contributed to the error. It then adjusts each weight slightly to reduce that error the next time.
So it's like the network is saying, I got this wrong. Let me tweak my understanding a bit.
Exactly. And this process happens thousands or millions of times with different examples until the network gets pretty good at the task. It's a bit like learning to play basketball. You shoot, miss, adjust, and try again until you improve.
I'm still terrible at basketball despite years of trying, but I see your point. So why does deep learning require so much computational power? Is it just because there are so many weights to adjust?
That's a big part of it. Modern deep learning models can have billions of parameters, those weights we talked about. But it's also because training often requires processing enormous data sets, sometimes millions of examples, and each pass through the data requires a ton of mathematical calculations.
Is that why GPUs are so important for AI now?
Absolutely. GPUs, graphics processing units, were originally designed for rendering video games, but it turns out their architecture is perfect for the kind of parallel computations needed in deep learning. They can perform thousands of simple calculations simultaneously, which is exactly what neural network training requires.
That's interesting, minus technology designed for games ending up powering AI breakthroughs.
It's one of those happy accidents in technology. And now we have specialized AI chips designed specifically for neural network computations, like Google's TPUs, tensor processing units, and various AI accelerators from companies like NVIDIA and AMD.
Does every model need to be trained from scratch? That sounds incredibly resource intensive.
Great point. This is where transfer learning comes in, which has been a huge advancement. Instead of starting from scratch, you can take a pre-trained model that already learned general features from a massive data set and then fine-tune it for your specific task with much less data and computing power.
So like teaching someone general cooking techniques first, and then they can learn to make a specific dish much more easily?
That's a perfect analogy. And transfer learning is why AI has become more accessible to smaller companies and researchers. They don't need to train massive models from scratch, they can build on existing ones.
Let's talk about some specific applications. You mentioned computer vision earlier. How exactly did deep learning revolutionize that field?
It was nothing short of a revolution. Before deep learning, computer vision systems relied on manually engineered features. Programmers had to explicitly code rules for identifying corners, edges, and other patterns in images.
That sounds tedious and limiting.
It was. The breakthrough came around 2012 with a CNN called AlexNet that dramatically outperformed traditional approaches in the ImageNet competition, a major image recognition challenge. Suddenly, neural networks could automatically learn the important features from data instead of requiring humans to specify them.
What kinds of computer vision tasks can these networks handle now?
It's quite impressive. Beyond basic image classification, this is a dog, this is a cat, they can perform object detection, identifying multiple objects in an image, and drawing bounding boxes around them. They can do image segmentation, essentially outlining each object pixel by pixel.
I've seen some medical applications too, right? Like analyzing x rays.
Absolutely. Medical imaging is a huge application area. Deep learning systems can now detect potential tumors in mammograms, identify eye diseases from retinal scans, and spot fractures in x rays, often with accuracy rivaling human radiologists.
That's incredible. What about autonomous vehicles? I'm guessing they use these technologies too.
They're completely dependent on them. Self driving cars use CNNs and other deep learning models to understand their surroundings, identifying pedestrians, other vehicles, traffic signs, lane markings, and so on. The cars are essentially covered in cameras and other sensors, all feeding data into these neural networks.
So, with all these amazing applications, what are some of the recent advances in computer vision?
One big area is visual understanding beyond just recognition. Systems now don't just label objects, but can understand relationships between them and even generate natural language descriptions of scenes. There's also been huge progress in 3D understanding from 2D images, video analysis, and action recognition.
Actually, I tried one of those apps that identifies plants from photos last weekend on a hike. It correctly identified a trillium flower I'd never seen before. It feels like magic sometimes.
I've used those too. I was hiking in Muir Woods last month and kept stopping every 5 minutes to identify another plant or mushroom. My friend Sarah almost abandoned me on the trail because I was slowing us down so much.
I've been hearing a lot about foundation models lately. What exactly are they, and how do they relate to deep learning?
Foundation models represent one of the most significant shifts in AI in recent years. Essentially, they're massive neural networks trained on enormous and diverse data sets, creating a general purpose system that can be adapted to many different tasks.
So instead of building specialized models for each task, you start with one big pre-trained model and customize it?
Exactly. Models like GPT Generative Pre-trained Transformer for text and DALI for images are trained on vast amounts of data from the internet. This general training gives them broad capabilities that can then be fine-tuned or prompted for specific applications.
How do these models actually work? Take something like GBT. How does it generate such coherent text?
At its core, GPT is a type of deep learning model called a transformer, which we mentioned earlier. It's trained to predict the next word in a sequence based on all the previous words. Through massive training on internet text, it learns patterns of language, grammar, facts, reasoning, and even some understanding of concepts.
And Dolly for images?
DALI combines language understanding with image generation. It uses a diffusion model approach where it gradually transforms random noise into a coherent image guided by the text prompt. The model learned associations between words and visual concepts during training.
These capabilities seem almost magical. What are the limitations we should be aware of?
There are several important ones. First, these models can generate content that sounds plausible but is factually incorrect. They also inherit biases present in their training data, which can lead to problematic outputs. And they lack true understanding. They're essentially sophisticated pattern matching systems rather than models with genuine comprehension.
I've definitely seen examples of AI confidently stating completely wrong information. It's concerning, especially if people trust these systems blindly.
Absolutely. I was researching a paper the other day and asked one of these models for citations. It gave me perfectly formatted, completely fictional papers and authors that don't exist. The problem is it all looks so legitimate.
What about ethical concerns with these foundation models?
There are many. Beyond the hallucination issue, there are concerns about copyright and ownership of the training data, the environmental impact of training these massive models, potential for misuse in generating misinformation or deepfakes, and questions about job displacement. Not to mention the concentration of power in the hands of the few companies that can afford to build these models.
It sounds like powerful technology that we're still figuring out how to use responsibly.
That's exactly right. These models represent extraordinary technological achievements, but come with equally significant responsibilities and challenges.
So, looking ahead, what's on the horizon for deep learning? Where is this field headed?
There are several exciting research frontiers. One major area is making deep learning more efficient. Current models require enormous computing resources and energy, which is both expensive and environmentally problematic.
I've read that training some of these large models can produce as much carbon as several car lifetimes. That doesn't seem sustainable.
It's definitely a concern. That's why there's significant research into more efficient architectures and training methods. Techniques like knowledge distillation, essentially creating smaller student models that learn from larger teacher models, are showing promise.
What about multimodal models? I keep hearing that term.
Multimodal models are a huge frontier. Instead of just handling one type of data, like text or images, these systems can process and generate multiple modalities. GPT-4 and Claude can now understand images as well as text. Models like Gemini and upcoming versions can handle text, images, audio, and even video in unified systems.
That sounds more like how humans process information. We don't separate our visual and auditory understanding.
Exactly. Our brains integrate information from multiple senses, and these multimodal models are taking steps in that direction. Another exciting frontier is self-supervised learning, where models can learn from unlabeled data by predicting parts of their input from other parts.
Like how a child might learn just by observing the world without explicit teaching.
That's a good comparison. Traditional supervised learning requires labeled data, which is expensive and limited. Self-supervised approaches allow models to learn from vastly more data without human annotation.
What about neuromorphic computing? I've seen that mentioned as a future direction.
Neuromorphic computing involves designing hardware that more closely mimics the structure and function of the brain. Current deep learning runs on traditional computing architecture that's not optimized for neural network calculations. Neuromorphic chips could potentially run AI algorithms with far greater efficiency.
Speaking of brains, is there any progress toward more general intelligence in AI?
That's the ultimate frontier, creating systems with more general intelligence rather than narrow capabilities. While we've seen models develop impressive capabilities on specific tasks, we're still far from anything resembling human-level general intelligence.
What would that even look like?
A generally intelligent I would be able to transfer knowledge between domains, learn new tasks quickly with minimal examples, understand causality rather than just correlation, and have some form of common sense reasoning. Current systems, despite their impressive abilities, still lack these qualities.
So we're not close to the sci-fi scenarios of general AI?
Not imminently, no, but the pace of advancement has surprised even experts in the field, so it's difficult to make long-term predictions. What we can say is that the next decade will see deep learning continue to transform industries and our daily lives in ways we're just beginning to imagine. Well, it looks like we've covered a lot of ground today on deep learning.
We sure have. To recap, we explored how neural networks are loosely inspired by the brain, with neurons that process inputs through weights and activation functions.
We looked at different types of neural networks like CNNs for visual data, RNNs for sequential data, and transformers that have revolutionized natural language processing.
We discussed how these networks are trained using backpropagation, requiring massive computational resources, which is why GPUs and specialized AI chips have become so important.
We explored breakthroughs in computer vision, from basic image recognition to advanced applications in healthcare and autonomous vehicles.
And we examined foundation models like GPT and DALL-E that are pushing the boundaries of what AI can do, along with their limitations and ethical considerations.
Finally, we looked at research frontiers, including more efficient architectures, multimodal models, and the long-term quest for more general intelligence.
What's next on AI Explained?
In our next episode, we'll dive into natural language processing, machines that understand us. We'll explore how AI systems process, understand, and generate human language, the technologies behind chatbots, translation services, and those large language models we touched on today.
That sounds fascinating. I'm particularly interested in how these systems handle the ambiguity and cultural nuances of human language.
We'll definitely cover that. Language is incredibly complex, and the journey to create machines that truly understand it has been full of challenges and breakthroughs.
Before we go, I have to ask, did your mom actually understand your napkin diagram of neural networks?
Let's just say she was very supportive and now proudly tells her friends her son does something with computers and math. Close enough, I suppose.
Better than my dad, who still introduces me as my daughter who talks about robots on the internet.
If you enjoyed this episode, please share it with friends or colleagues who might be interested in understanding deep learning.
We're continuing our journey through artificial intelligence by examining a technology that's quite literally changing how machines see the world.
That's right, we're diving into computer vision, the field that gives AI systems the ability to interpret and understand visual information from the world around them.
It's fascinating how something that seems so effortless for us humans, like recognizing a friend's face or identifying objects in a photo, has been such an enormous challenge for computers.
Absolutely. Our brains process visual information so naturally that we don't appreciate how complex the task really is. I mean, I can glance at my desk and instantly recognize my cough mug, my notebook, that plant I've somehow kept alive for 3 months.
3 months. That's a personal record for you, isn't it?
Hey, I'll have you know I'm getting better. This one hasn't turned brown yet. But seriously, teaching machines to see has been one of the most challenging and rewarding areas of AI research.
Let's start by exploring what makes computer vision so challenging. Why is visual perception so difficult for machines?
I think people underestimate how incredibly complex vision is. When we see something, our brains aren't just passively receiving an image, they're actively interpreting and making sense of huge amounts of visual data.
Exactly. We're not just identifying objects, but understanding their relationships, dealing with variations in lighting, angle, size, occlusion, when objects are partially hidden, and so much more.
And all of this happens instantly for us. I don't need to think, that round object with a handle that contains liquid is processing, a coffee mug. It's just immediate.
Computer vision has gone through a fascinating evolution to address these challenges. The early approaches were very rule based, with researchers trying to hand code what, for instance, the edges of an object might look like.
I remember reading about those early systems. They'd try to identify specific features like corners or edges using mathematical formulas, right?
Yes, and while those approaches had some success in controlled environments, they struggled terribly with real world complexity and variation. The breakthrough came when we shifted to data driven approaches, especially deep learning.
Which we covered in our episode on deep learning, using neural networks trained on massive data sets rather than explicitly programming rules.
Exactly. Your data has been absolutely crucial. Projects like ImageNet, with millions of labeled images, fundamentally transformed what was possible in computer vision.
So let's dive into image classification and recognition, probably the most fundamental computer vision task. How does a system actually identify what's in an image?
At its core, modern image classification uses convolutional neural networks, or CNNs, which we touched on in our deep learning episode. These networks learn to identify increasingly complex features in images.
Right, the early layers might detect simple edges and textures. Middle layers might find more complex patterns like eyes or wheels, and deeper layers identify entire objects or scenes.
But ImageNet competition really catalyzed progress in this area. When AlecNet dramatically outperformed traditional methods in 2012 using deep learning, it triggered a revolution in the field.
I was reading that modern systems can now identify thousands of different object categories with accuracy that sometimes exceeds humans. That's pretty mind blowing.
It is impressive. And a key technique that's made these advances more accessible is transfer learning, taking models pre trained on massive datasets like ImageNet and fine tuning them for specific applications.
I actually used transfer learning for a project last month. I needed to identify different types of birds that visit my backyard feeder, and instead of training a model from scratch, I fine tuned a pre trained one with just a few hundred images of local bird species.
That's a perfect example of how these technologies have become more accessible. A few years ago, that project would have required specialized expertise and significant computing resources.
Exactly. Though I did have an embarrassing moment when my system kept classifying my neighbor's tabby cat as a small mountain lion. Mrs. Peterson was very concerned when I told her.
Moving beyond basic classification, let's talk about object detection and segmentation. These tasks go further by not just identifying what's in an image, but where it is and precisely outlining it.
So instead of just saying there's a dog in this image, these systems can draw a box around the dog or even outline it pixel by pixel.
Exactly. Object detection locates multiple objects in an image and draws bounding boxes around them, while instant segmentation goes further by creating precise outlines of each object, what we call masks.
I noticed this technology in my phone's camera app. It can recognize people and objects in real time as I'm taking photos.
Those are built on architectures like RCNN, Fast RCNN, Faster RCNN, and YOLO, which stands for You Only Look Once, a particularly efficient approach that can perform detection in real time.
These capabilities seem to have endless applications. I saw a retail system recently that automatically tracks inventory on store shelves by analyzing camera feeds.
Retail is a huge application area. These systems can monitor stock levels, detect misplaced items, and even analyze customer behavior. They're also transforming security and surveillance, manufacturing quality control, autonomous vehicles.
And healthcare too, right? I read about systems that can detect potential tumors in medical images.
Absolutely. Medical imaging is one of the most impactful applications. AI systems can now identify potential abnormalities in X rays, MRIs, CT scans, and other medical images, often with accuracy comparable to human radiologists.
Let's talk about video analysis. How do computer vision systems handle the added dimension of time?
Video analysis adds significant complexity because systems need to process not just individual frames, but understand how they relate over time. This includes tracking moving objects, recognizing actions, and understanding activities.
I imagine tracking is particularly important for applications like surveillance or sports analytics.
Definitely. Tracking algorithms follow objects or people across frames, maintaining their identities even when they're temporarily obscured or move out of frame. This is crucial for everything from security systems to analyzing athlete performance.
What about action recognition? I noticed my social media apps seem to understand the content of videos I post.
Action and activity recognition is a rapidly advancing area. Systems can now identify specific actions like running, jumping, or cooking by analyzing patterns of movement over time. The most advanced systems can even recognize complex activities involving multiple people and objects.
I tried an app last week that automatically created a highlight reel for my vacation videos. It somehow identified the most interesting moments without any input from me.
That's video summarization, using computer vision to identify significant or interesting segments in longer videos. It's particularly useful for security footage, sports coverage, and personal videos.
Though it did seem bizarrely fixated on capturing every time I tripped over something or made an awkward face. I'm beginning to think the AI has a sense of humor.
Or maybe you're just extraordinarily clumsy, Leo. Another fascinating area is 3D vision and spatial understanding. Most images and videos are 2D, but the world we live in is three-dimensional.
That's a fundamental challenge, right? How do systems understand depth and spatial relationships from flat images?
Exactly. One approach is depth estimation algorithms that can predict how far away different parts of a scene are, even from a single 2D image. It's remarkable how accurately modern systems can do this.
Is that related to how my phone's portrait mode blurs the background of photos? It seems to understand which parts of the image are further away.
That's a perfect example. Another critical technique is 3D reconstruction, building complete three-dimensional models from multiple 2D images or video frames.
I've seen apps that can create 3D models of objects just by walking around them with your phone camera. The technology seems almost magical.
It's incredibly sophisticated. And then there's SLAM, simultaneous localization and mapping, which is crucial for robotics and augmented reality. It allows systems to build a map of an unknown environment while simultaneously tracking their location within it.
That's how my robot vacuum knows where it's already cleaned and where it still needs to go, right?
Exactly. And the same core technology powers AR experiences on our phones and headsets. It's what allows virtual objects to appear as if they're actually part of the physical environment around you.
I tried an AR furniture app when I was redecorating my apartment last month. It let me see exactly how a new couch would look in my living room before buying it. Saved me from making a terrible color choice.
Let me guess, was it that neon green one you showed me a picture of?
I stand by that it would have made a bold statement.
Let's move to one of the most talked about areas in computer vision right now, visual generation and editing.
You mean like Dolly, Midjourney, and Stable Diffusion? The systems that can create images from text descriptions?
Exactly. These text-to-image models have captured public imagination because they demonstrate a kind of creativity that many people didn't expect from AI systems.
The technology behind them is pretty fascinating. They're basically learning the relationship between images and the language used to describe them, right?
That's right. Most modern systems use diffusion models, which work by gradually removing noise from a random starting point, guided by the text prompt. We covered this briefly in our deep learning episode.
Beyond creating images from scratch, these systems can also edit existing images in incredibly sophisticated ways.
Yes, capabilities like inpainting to fill in missing parts of images, outpainting to extend images beyond their original boundaries, and style transfer to apply the artistic style of one image to another have become remarkably powerful.
Video generation seems to be the next frontier. I've seen some early examples that are mind-blowing, creating short videos from text descriptions or even extending existing clips.
The progress in this area has been astonishingly rapid, but it also raises important ethical questions about synthetic media, doesn't it?
Absolutely. The potential for misuse through deepfakes and disinformation is concerning. And there are complex questions around copyright, consent, and the impact on creative industries.
These are issues we'll explore more deeply in our episode on AI ethics, but it's worth noting that alongside these concerns, these technologies are opening up new creative possibilities and accessibility options for people who might not have traditional artistic skills.
I'd like to talk about a few real-world applications of computer vision that showcase just how transformative this technology can be.
Let's start with one of the most visible examples, autonomous vehicles. Self-driving cars rely heavily on computer vision to understand their environment.
They're basically covered in cameras and sensors, right? All feeding data to AI systems that need to identify everything from other vehicles to pedestrians, traffic signs, lane markings.
Exactly. And they need to do this in real time under constantly changing conditions, different weather, lighting, traffic scenarios. It's an extraordinarily complex problem.
Healthcare is another area where computer vision is making a huge impact. Beyond the diagnostic imaging we mentioned earlier, I've read about systems that can monitor patient movements to detect falls in hospitals or track surgical procedures to ensure safety protocols are followed.
Agriculture is employing these technologies too, using computer vision-equipped drones to monitor crop health, detect diseases, and optimize irrigation and fertilization.
I just read about a system that can identify individual cows in dairy herds by their unique hide patterns, tracking their movements and behaviors to monitor health and productivity.
Facial recognition is perhaps the most well-known and controversial application, used everywhere from unlocking smartphones to security systems and law enforcement.
The capabilities are impressive, but the privacy and civil liberties implications are significant. There's been a lot of pushback against widespread deployment of these systems.
Absolutely. This is another area where technical capabilities have outpaced our ethical frameworks and regulatory systems. We're still figuring out as a society how to balance the benefits with the potential harms.
Before we wrap up, let's talk about some of the current challenges and limitations in computer vision.
One significant challenge is adversarial examples, specially crafted inputs that can fool AI vision systems in ways that would never trick a human.
I've seen those, like how adding certain patterns to an image can make a system confidently misclassify a panda as a gibbon, even though to human eyes it's clearly still a panda.
Exactly. These vulnerabilities raise serious concerns for safety-critical applications like autonomous vehicles or security systems.
Computer vision systems also still struggle with unusual scenarios or edge cases, right? Things they haven't seen in their training data.
That's a fundamental limitation. Despite their impressive capabilities, these systems lack true understanding of the physical world and its constraints. They don't have common sense reasoning about how objects behave or interact.
I remember reading about a self-driving car that got confused by a truck with a mural of a street scene painted on its side. The system couldn't distinguish between the painted road and an actual road.
That illustrates the problem perfectly. And then there's the issue of bias in these systems, which can reflect and amplify biases in their training data.
Like facial recognition systems performing worse on certain demographic groups because they were underrepresented in the training data?
Exactly. These issues highlight why responsible development and testing of computer vision systems is so important, especially as they become more integrated into critical infrastructure and decision-making processes. As we wrap up today's episode on computer vision, let's recap the key points we've covered.
We explored why visual perception is such a complex challenge, requiring systems to interpret and understand visual information in context, deal with variations in lighting, angle, and appearance, and make sense of a three-dimensional world from two-dimensional images.
We traced the evolution of computer vision approaches from early hand-engineered feature detection to modern deep learning methods that learn directly from data.
We examined core capabilities like image classification and recognition, which allows systems to identify what's in an image, object detection and segmentation, which locate and outline specific objects, and video analysis for understanding motion and activity over time.
We discussed 3D vision and spatial understanding techniques that enable depth perception, 3D reconstruction, and applications like augmented reality.
We looked at the rapidly advancing field of visual generation with systems that can create and edit images and videos with unprecedented quality and control.
And we explored real-world applications across domains like transportation, healthcare, agriculture, and security, while acknowledging important challenges around adversarial examples, handling edge cases, and addressing bias.
It's incredible how far computer vision has come in just the past decade. Tasks that seemed impossible for machines not long ago are now routine.
And yet, we're still just beginning to tap the potential of these technologies as they continue to advance and become more integrated with other AI capabilities. We'll likely see applications we can barely imagine today.
What's coming up next in our AI Explained series?
In our next episode, we'll be exploring AI in industry, transforming business and services. We'll examine how AI technologies, including computer vision and the other systems we've discussed, are revolutionizing major sectors like healthcare, finance, retail, manufacturing, and more.
That should be fascinating, seeing how these technologies move from research labs into practical, real-world applications that are changing how businesses operate and how services are delivered.
Exactly. We'll look at concrete examples of AI implementation across industries, the challenges organizations face in adoption, and how the relationship between humans and AI systems is evolving in workplace settings.
I'm particularly interested in discussing how these technologies are augmenting human capabilities rather than simply replacing jobs, that tension between automation and augmentation.
We'll definitely cover that. It's such an important aspect of how AI is being integrated into industry.
If you found today's exploration of computer vision illuminating, please share this episode with friends or colleagues who might be interested in understanding how machines perceive and interpret visual information.
And join us next time as we continue our journey through the world of artificial intelligence with AI in industry, transforming business and services. Thanks for listening to AI Explained.